Uniform electric field. Up until now, we've dealt with electric fields and potentials due to individual charges. What is more interesting and relates to more practical applications is when you have configurations of a massive amount of charges. Let's begin by examining two infinite planes of charge, here's one and here's the other, that are separated by a small distance. The planes have equal amounts of charge, with one plate being charged positively and the other one being charged negatively. The above is a representation of two infinite planes. It's rather hard to draw infinity. By applying Gauss's law, a law that will be learned in AP Physics C, it is found that the strength of the electric field will be uniform between the planes. It will have the same value everywhere between them. And the electric field outside the planes will be zero. A positive charge placed within the field will move from top to bottom. In this case, the work done by the electric field is positive. The field is in the same direction as the charge's motion. The electric potential energy of the system will decrease, and this is directly analogous to the movement of a mass within a gravitational field. Point charges have a non-uniform field strength. See the electric field arrows, they get farther away from each other the farther out you go. Right here, they're kind of close. Here they spread out. So, the field weakens with distance. Only some equations we will learn will apply to uniform electric fields. Or see how these are all the same distance apart and the same length? That means the electric field is constant. For the parallel planes, the electric field is generated by the separation of charge. You've got all positives up here and all negatives down here. The field lines originate on the positive charges and terminate on the negative charges. The difference in electric potential, voltage, is responsible for the electric field. The change in voltage is defined as the work done per unit charge by an external force against the electric field. We did that a few topics ago. Therefore, energy is being put into the system when a positive charge moves in the opposite direction of the electric field. So here we have a positive charge and it's moving this way against the electric field, which means somebody's applying an external force to it. It's also the same when a negative charge moves in the same direction of the electric field. Positive work is being done by the external force, and since the positive charge is moving opposite the electric field, negative work is being done by the field. A useful equation relating voltage in a uniform electric field can be derived. The electric force on a positive charge released in a uniform electric field is constant. Therefore, the work done by this field is WE, and E stands for electric field this time, not external. External would be EXT. So the work is F delta X, and the force is just QE, delta X. Since the electric field is conservative and work done by this field is equal to the negative change in electric potential energy, we have this expression here. And then, what's delta UE? Why, that's Q delta V. So we have work done by the electric field is minus Q delta V. The same electric field force is performing work. It's just expressed in two different equations. We're allowed to set the two of them equal to each other. So we have work is QE delta X, and work is also minus Q delta V. Set them equal to each other. We have QE delta X equals minus Q delta V, and we want to solve that for E. So first we divide through by Q, and they cancel out, and then we divide through by delta X, and we have E is equal to minus delta V over delta X. We've already shown this graphically, but now we're showing it in an equation. And what does that tell us? The negative sign indicates that the electric field lines point in the direction of decreasing electric potential. When solving these problems, we're frequently only asked for the magnitude of the electric field, so we don't need to worry about the negative sign. But just remember, that negative sign tells you which way the electric field is pointing. It's pointing in the direction of decreasing electric potential. This equation only applies to uniform electric fields. It follows that the electric field can also be shown in terms of volts per meter. Why? Well, this is volts, this is meter, in addition to newtons per coulomb. Let's see why that works. So we have volts per meter, and what's a volt? Well, that's a joule per coulomb. Now we're dividing that by M. A joule per coulomb over meter, well, a joule is a Newton meter. So we have Newton meter divided by coulomb over meter. What do we have next? We have the Newton meter over coulomb. Well, divided by meter, the meters cancel out, and we wind up with newtons per coulomb. The units are equivalent. So volts per meter, same as newtons per coulomb. What is the magnitude of the electric field between two metal plates 5 millimeters apart if the potential difference between them is 240 volts? So we have given the difference in potential is 240 volts. The distance between the plates is 5 millimeters, which we have to convert into meters. So we move the decimal place over 3 and we get 0.005 meters. We use our equation here, and we're going to take the absolute value because we're just interested in the magnitude. So we have 240 volts divided by 0.005 meters, and we get 4.8 times 10 to the fourth newtons per coulomb, or volts per meter. They're equivalent, those units. An electric field of 440 volts per meter is desired between two plates which are 4.5 millimeters apart. What voltage should be applied? Here's our electric field, and this time instead of newtons per coulomb, it's volts per meter. Same thing. We have to convert the distance between the plates to meters, and you move the decimal over 3 to convert millimeters to meters. And once again, we're just looking for an absolute voltage, so we take the magnitude here, which is the absolute value of both sides. We multiply both sides by delta x because we want to solve for delta v. And we have delta v is equal to the electric field times the distance between the plates, and we get a voltage difference of 2.0 volts. A uniform 450 Newton per coulomb electric field moves a plus 3.4 microcoulomb charge 10 centimeters. How much work is done by the electric field? We start with some unit conversions. 3.4 microcoulombs is 3.4 times 10 to the minus 6 coulombs, and 10 centimeters is 0.1 meter. You move the decimal over 2 places to the left. The work done by the electric field is QE delta x. Here's our Q, here's the electric field, here's the displacement, and we get the work is 1.5 times 10 to the minus 4th joules. Let's wrap up the equations we've used for uniform and non-uniform electric fields. The ones on the left we summarized earlier. These are the big four, and these are used only with point charges. Equations with K in them are for point charges only. You can have 1-point charge, 2-point charge, 3-point charges, but as long as you have a very small number of them, you can work with these. So the force, Coulomb's law, the electric field, the potential energy, and the electric potential or voltage. Then we can use these equations in any situation. F is equal to QE, or work done by an external force is Q delta V. And then finally, for uniform electric fields, we can use the work done by the electric field is QE delta X, and the electric field is equal to minus delta V over delta X.